Welcome everyone to the IDIADA Virtual Proving Ground webinar. Thank you for joining us today. We're going to explain the best methodologies we have in-house to support our development of vehicle dynamics and comfort performances by using our Proving Ground digital twins and how efficient and good things has provoked in our methods. So let's start with an introduction to our speakers. I'm Javier Gutierrez, product coordinator of the Virtual Proving Ground product, as well as Vehicle Dynamics CAE. I've been in IDIADA for 8 years, and I'm mainly working in the vehicle dynamics simulation work. So I've been one of the main users of the Virtual Proving Ground in our department. Please, Gunnar.
Yeah, I'm Gunnar Grefe, CEO and founder of 3D Mapping Solutions. Our task is to precise the Proving Ground digitally and provide the data for all possible simulation or co-simulation or simulator applications.
Thank you, Javier, and welcome everybody to this webinar. My name is Alfonso Square. I am project manager in the Vehicle Dynamics department, and I work as an integration leader for projects involving vehicle dynamics functional development.
Hello, my name is Guido Tosolin. I am responsible in IDIADA for vehicle dynamics simulations and development.
So in today's webinar, we'll go through main characteristics of the digital twin of Applus IDIADA Proving Ground. But on top of that, we'll go through 4 use cases. First, we'll start how in the early stages of a project, we use the 2D profiles in order to generate good seeds in order to get better optimized results with reduced number of iterations. Secondly, we'll describe how we apply the virtual proving grounds and the road geometry in a more specific, in a more precise way for comfort performance development. In third place, we describe the application of the virtual proving ground and its seamless integration into the driving simulator activities. And finally, we'll see how critical the road geometry is for a proper load cascading and to be used in virtual fatigue predictions, and how this is quite critical. So let's start briefly with an introduction to the company and to the department we work for, and then we'll go through main characteristics of the virtual proving ground. So Applus IDIADA is a global development partner with more than 30 years of experience in the automotive industry, and it supports its clients in activities related to design, engineering, and testing activities, services. Our success is based mainly on 3 pillars, which are highly experienced engineers, state-of-the-art testing and engineering facilities, and finally, a constant drive towards innovation of the company. As we can see in the images in the slide, IDIADA is able to supply, to support our clients in all the phases of the development project, as well as in different performances. As of today, we have presence in physical presence in 24 countries around the world, with main technical centers in Spain, India, China, the UK, US, Brazil, and that's it. And with a total number of headcount of approximately 2,600 people. Related to the vehicle dynamics department, it comes with more than 20 years of experience in chassis engineering and testing activities, with a deployment around the world of an international team of around 200 people. And we can support our clients worldwide. We have been traveling to any place around the world for supporting both engineering and testing activities, and with permanent basis similar to the company in Spain, UK, Germany, Italy, Czech Republic, China, India, Brazil, and the US. Similar to the company, we have a very OEM-oriented approach with flexible and adaptable to every customer request and need. And specifically for the vehicle dynamics and comfort performance, we are able to support our clients and our projects from the concept phase to the design of phase, and in the development of these activities, the virtual proving ground has played a key role that we'll be able to describe in the next slides in order to be able to support us to develop safer environments to develop our activities, more close to reality, and obviously more efficient as well. So let's start with some more details about the Spain virtual proving ground activities and the data itself. So virtual testing is clear that it's becoming more and more important to solve our engineering challenges, especially now that we all tend to use data-driven approaches, and this helps to generate more and more data that is a perfect complement to testing data, because simulation can generate all this extra data that is needed. The virtual proving ground concept was kicked off as an initial internal need, but over the years, the users of the proving ground have started to use it as well. And on top of that, some of the main software suppliers around the world has seen the interest and is helping us to commercialize this on our behalf. If we talk a little bit about history and how this was developed inside IDIADA, the initial stages started in 2012, when it was decided to start with the first scan activity, mainly focusing one of the applications, which was the road representation for virtual durability applications and comfort. The result of this was the generation of CRG, open CRG files that were extensively used internally for our projects, as well as some initial users. In the second step, around 2016, we detected that the number of applications were growing, and also we need to set up a method in order to commercialize this properly to our clients. So this ended up having the definition of the partner strategy and the IPR concept, the intellectual property rights concept, that we'll define a little bit more later. The result of this was a second scanning campaign where it was mainly with 3 applications in mind, and more to come that we'll define as well later, which is again the virtual durability roads, surfaces, driving simulator applications with 3D environments, and finally the HD maps for ADAS and autonomous development vehicles. And since mid of the year of 2018, we have this data available to be able to be used both internally and externally. And right now we are in a more growing phase, maturity phase, where we are trying to add more and more tracks with different formats, looking for more applications and extending the number of partners in order to supply it to support all the needs required by our users. If we do a little bit of a sum up of what have been the main internal engineering applications so far internally at IDIADA, so starting from single raw information, single source of information, as we have commented, we have used mainly virtual surfaces for durability and comfort and MDH applications in different kind of formats, CRG, RGR, 2D profiles. A second pillar is based on the driving simulator 3D environment that can be also represented in different formats. And finally, the third block, it's mainly composed by the HD maps in a format of OpenDrive, Carla, or any other. It's important to mention that the different formats include different levels of information and different accuracies, and the level of standardization between them is also not exactly the same. And another point to mention, important, is that we have been using internally at IDIADA this data from 2012, so this has built a lot of trust on the data over the years at IDIADA, and this can be certainly extended to our potential clients. So now let's describe a little bit what was the scanning and post-processing process of the data, and thus I would like to pass the word to my colleague Gunnar Greff, who will explain from 3D mapping how these activities were performed for IDIADA. Please, Gunnar.
Yeah, thank you very much. As you have already mentioned, 3D mapping was very thankful to have the task to digitize the IDIADA proving ground and also roads around IDIADA. And so our task is that we perfectly digitize, in the first step, the real road to bring it as perfect digital twin into the simulation and simulator environment. And to do this, we use very sophisticated survey vehicles, which have at first component a movement compensation by an inertial system, giving you a part of 1,000th of a degree as accuracy for any kind of vehicle movement. And we scan the surfaces and all the surroundings and all the road corridor with scanner data with a relative accuracy in the range of 0.3 to 0.5 millimeter. So it's a very, very precise digitalization. And from there, we bring it to all kinds of simulator or simulation environments, and we produce especially very high precision, high resolution road surface models in OpenCRG or RGR format, so that you can directly use this for simulation for vehicle development. And the sensors we use in the vehicle to precisely digitize the road corridor are, of course, as the main sensor nowadays, the scanners. We have always 2 scanners on each vehicle, so that the scanners not only deliver a redundant information, it's also the super perfect quality control. So if we have to prove, for example, for a very high frequency Belgic block test track that the surface model resulting in the CRG is perfectly right, then we can prove by the 2 scanners that there's an 0.5 millimeter height accuracy in the relative surface model. And of course, this is accompanied by calibrated cameras, which allow us to also survey any kind of point object, deliver any kind of textures, and to adjust to all technical requirements, we have color cameras as well as infrared cameras. And for texturing, some providers also use our panoramic images. So this is mainly for all the kinds of simulation and simulator environments. And what's brand new is that we also may add radar reference measurements, so that each pole, each object, everything visible in, let's say, in the digital twin also can have a radar reference measurement for very precise radar simulation. When we digitized the IDIADA proving ground facility, then of course you see that we digitized all roads, everything around, everything inside, and as impressions you see here the camera data with color cameras. You see in the upper left, the lower left corner, you see an orthophoto of the scanner data, which is also used for texturing the surface, and in the lower right, you see an image out of the scanner data. And this is an animation of what we call raw data. So this is the let's say, animated point cloud of the scanner data in original resolution. In this scanner data, you see this Belgic block track in very perfect raw data resolution. The original resolution, it's, let's say, in the range, any 2, 3 or 3 millimeter, you have a point, and each survey point has a very low noise below 1 millimeter, so that based on this data, for example, a precise OpenCRG can be produced, but also OpenDrive or Road5 or other simulation or HD map data formats can directly be derived on the basis of the corridor digitalization. If you look on the processing chain, let's say the quickest and easiest part is always the mapping itself. Then the data processing is the quality part. So in the data processing part, we take care that all the quality of everything we are doing is simply perfect, because all the simulation results, of course, depend on this quality management step. Then we extract all the required information. For example, we vectorize all the objects, we vectorize and all the lines, the markings, the curves, and so on. And then out of that, out of the let's say, resulting as-built plan, we produce an Ultra HD map. And the Ultra HD map is not only an as-built plan, but the digital twin as OpenDrive or Road5 always contains all the road logic, all the semantics, everything you directly need to drive on with an autonomous driving vehicle or within a simulation or within traffic simulation or any kind of application. And the most important thing is that the data from the beginning is sensor simulation accurate. So it's not only nice for driving, which is of course one application, it's also nice for proving, validating, and in the final end, giving a complete driving license to the autonomous driving car, which is mainly done on the basis of an Ultra HD map and all derived simulation processes. What we did for IDIADA was, of course, delivering the basic data for the simulator applications. So the simulator, let's say, software or hardware packages, the driving simulators, they are all based in the applications on the precise digital twin, on the precise digitalization of the proving ground. We also delivered Ultra HD map data so that there's a complete as-built setup, but also this contains all the complete semantics, everything you directly need to drive on the intelligent map. And of course, we can provide the 3D environments for very different levels of resolution, so that all kinds of different applications with the complete bandwidth which need a 3D, from very simply generic to very high-end photorealistic, can be provided. And what's also possible nowadays is a very quick survey and update service. This goes for existing maps as built as well as for temporary setups. So the typical application is that on the proving ground, someone has a temporary setup which he uses for a certain edge case evaluation for autonomous driving, and then we may come by, survey it, and directly deliver the HD map results, so it's simulation proof. And a very specific additional feature, which is also available nowadays, is a super high resolution CRG available for very high-end noise or frequency analysis applications, as well as for chassis dynos. There we can produce, if required, a 1x1 millimeter CRG. The regular resolution, of course, for CRGs is 5x5 millimeter for most applications in vehicle dynamics, and 5x5 centimeter or 10x10 centimeter grids for high-speed applications where you need, for example, on a high-speed oval or something like that. Yeah, thank you very much.
Thank you, Gunnar. So now that we have covered the process of generating the data, let's talk a little bit more about the data itself and the main characteristics of the different tracks that we have digitalized. Before that, let's go through this graph where we try to explain the majority of the applications that the data allows us to do. So starting from a single source of data produced by 3D mapping, some of the main applications are the surface definition as a macro texture concept, mainly for applications like durability, comfort, and NVH. Secondly, the driving simulator, as we commented, and the HD maps for ADAS and autonomous driving testing and simulation activities. In fourth place, we can also discuss about tire development activities, where the microtexture of the surface can also be digitalized and used for simulation activities, and also some other activities that have been supporting traditional proving ground maintenance activities, like measuring of mu coefficients or granulometry or any other activities supporting the proving ground maintenance services. On top of that, any other customized request that a user may have from the data, we can think of it as to support, for example, the design of new roads, variation of the existing roads, etc. So now let's talk a little bit about the available tracks, both internally and some of the external routes that have also been digitalized and are perfect complements to the tracks inside IDIADA. Let's start with the general road, which is the generic road that connects all the rest of the tracks inside IDIADA. It has more than 5 kilometers, and it's very good also for performance evaluation, mainly in the straight line stability and the lower range of the speeds. The high radius curves also allows to evaluate the steady state cornering, and as well as the straights helps on the on-center handling and steering evaluation. There are some interesting bumps on top of it that supports the evaluation of primary ride and body control, especially in the north, in the top left curve, as well as it's also very much used for ADAS testing, especially on the straight lines. And this track is, as of today, available both as a surface model and a driving simulator model. Secondly, we have the high-speed circuit that has more than 7.5 kilometers and a constant width of 4 lanes, and it's available as a surface model and an HD model. As we can see, for example, in one of the applications recorded in the video in the top right of the slide, where the electronics department were using it just to support the positioning of the vehicle inside the track. A principal application of this track is similar to the ones of the general road, but at lower, much higher speeds. It's also a good reference for, or a good basis for rolling resistance and cost down tests. This asphalt is of a high quality and is being constantly used as MBH reference. And as we commented, it's also very much used by the ADAS and connecting autonomous development teams for algorithm development on top of them. Next, we have the fatigue tracks. We have been a key player on our virtual fatigue activities. It consists of more than 3 kilometers of different combination of different kind of surfaces, like Belgian blocks, waterways, washboards, body-mounted road, etc., that supports the activities of accelerated durability cycles in fatigue development. It combines both the straight lines and turns, which are important in these durability cycles. And it also includes an area specifically for misuse events with different severities, different curves at different heights. The following is the dry handling track, which is a typical kind of circuit track at IDIADA. It has more than 2 kilometers and a constant width of 7 meters, and available for offline simulations as a surface model, and also for online simulations in our driving simulator and big grid format. As of principal applications, it's mainly used for global handling, stability, and lap timing applications. The next are track number 3 and 7, which is a combination of deterministic and random surfaces for comfort evaluation. It also consists of more than 3 kilometers of different combinations, also different kind of impacts and viscosities of the road, and they're mainly available for online and offline simulations as well. It supports the evaluation of primary and secondary road, the road holding, body control, and also the impact field on different deterministic inputs, both positive and negative, manhole covers, highway joints, etc., as well as different random roads like the rough road, the body-maintained road, and other kind of surfaces. And finally, we wanted to present one of the external roads that is a key play in our driving simulator, which is a road called Ajuncosa, which is more than 6 kilometers and is very close together, like 5 minutes drive. And it's a public winding road with several curves up and downhill. And it's quite interesting. It's a perfect complement for our dry handling track to have a more realistic road kind of event for the evaluation of handling, steering, and body control performances. Now that we have described the main characteristics of the tracks, let's go a little bit how the potential users can get access to that. So the idea from IDIADA is to provide a simple worldwide access either through IDIADA or partners, as we discuss in the next slide, the main differences. From the same source of data, there are two possibilities, either through partners or through IDIADA through an intellectual property rights model. We always try to have a seamless integration for majority of the softwares that our customers use, and also having an extra flexibility on format customization for those non-traditional applications. And we want to be covering as much as possible formats, content, applications, and those require accuracies for each application is needed. So two main blocks on how to access to the data, mainly the general type of access through our partners, and we're constantly looking for extra partners that can support the use of our tracks with our proving users. What they provide is a limited in time granted access to up-to-date, accurate, and encrypted data. And it's available in different formats provided by these partners in the different well-known formats that they distribute their models. As a second option, which is a type of exceptional type of access, is this intellectual property rights contract directly through IDIADA. And this is sessional because it's used when the general case does not fit the needs. It's exactly the same, the limited in time granted access to data, but in this case, instead of encrypted data, we're talking about open format data. And as being open format, we have more flexibility to customize the data it's shared exactly according to the needs from the different clients. Just to finalize this introduction, I would like to show this slide with us a summary of what is up to as of today available as formats and what the other tracks that we are working to build the different formats of it. It's interesting to mention as well that we have published a new website where it tries to sum up also these main characteristics of information of the virtual program, and you can check at any time. There's one track that we have not commented before, which is the ADAS and CAP track. That is a very recent track that was not available in the last scan campaign, but we're working right now into the development of these tracks virtually. So with no more introduction, let's jump now into the use cases of the vehicle dynamics applications. So now I would like to share the word with my colleague Alfonso Square, who will guide us to the early stages concept design activities.
Thank you very much, Javier. Okay, so let's start now with the real applications of the virtual proving ground. And first, I would like to give an overview about the general process of the vehicle dynamics virtual development. So the first point to understand is why we do virtual development. And our objective is to provide chassis component specifications that are justified from the point of view of the functional performance of the vehicle. And the way to justify those specifications is by comparing the vehicle test results or key performance indexes obtained from the simulation results with some predefined targets. So here it is our first challenge. The first challenge is to define right and handling targets and KPIs that are based on meaningful scenarios that are representative of the vehicle use. And of course, these targets and KPIs need to work for both simulation and real testing. Also, the intention of doing simulation is to minimize the number of components to be tested in physical tuning. However, moving from the physical to the virtual development implies dealing with, again, a high number of simulation results, load cases, KPIs, model parameters, etc. And we see that the number of model parameters might depend on the model complexity. And we will see some applications and examples later on. But what it is becoming more and more important is the use of some optimization tools that they help us to guide the process of validating this performance and model parameters. In the end, the reality is that also at early stages of the development, we do not have very much information of the vehicle. We still need to start sharing specifications with suppliers and other teams. And managers are asking us to give proof of the feasibility of the concept, also with low effort and in short time. So how do we tackle this at IDIADA? Our proposal is to use a MATLAB-based tool that creates this link between the performance targets definition, the simulation, and the chassis specification. So in the end, it facilitates the application of the methodology that we will be explaining later on. This a tool, we call it the MTC, which stands for Model-Based Target Cascading Tool. And what you can see in the main is the main interface of the tool, which is designed to provide an efficient workflow and guidance for users that have a minimal level of expertise. And the tool consists on three main parts. And these parts, we will describe it in a minute, but these parts are a simple model, a selection of the scenarios and KPIs, and an optimization part that runs these multiple iterations of the model using the same load cases and finding the best compromise of performance. So the key point here is everything is integrated in one single tool. Okay, regarding the model. The model is a 10 degrees of freedom model generated in MATLAB, and it allows to simulate both lateral and vertical dynamics for the assessment of ride and comfort and handling together. The tool is compatible with magic formula tire models, and it considers a specific tire contact modeling, as you can see here, that takes into consideration the tire radius, and this is done to have a better correlation of the ride and comfort simulations. Then the next part would be the scenarios. And here we need to say that it is known that resolving the conflict between ride and comfort and handling is probably the main challenge when tuning a vehicle or setting targets. Consequently, it makes sense that the process of cascading includes load cases for both areas of performance. And here you can see that the tool includes 5 load cases. In the case of handling, the load cases are representative of steady state cornering and transient lateral dynamics. And these are load cases 4 and 5. And in the case of ride and comfort, the tool considers 3 load cases that are used to evaluate primary ride and comfort, input harness, and secondary ride. Javier, next, please. Okay, and it's these 3 load cases when we find the strong link with the IDIADA virtual proving ground. The first load case represents a long bump, but it is similar to what we can find in our general road. The impact harness road input is part of our comfort track number 7, and the rough road is our badly maintained road that is part of our track number 3. How are these roads defined and used in the simulation? These roads profiles are defined by using 2D vectors of data points that are obtained from the 3D scan data that it was explained before. And so they contain basically vertical and longitudinal coordinates of the road points. And it is this simplified road model definition, in addition to the tire contact modeling that we mentioned before, which provides a more realistic estimation of the tire forces and hence a better performance prediction, especially for ride and comfort. Okay, now let's talk about the real use case. And now, in this example, is with regards to a project where IDIADA was supporting the development of a low-cost CUV vehicle for the Indian market. And in this project, we had the discussion about the need of including a front anti-roll bar in the vehicle or not. So the objective of these activities were, on one side, to confirm the need of the anti-roll bar, and on the second side is basically to confirm the targets of the vehicle based on that concept definition. So work with both things together. To do this, we tried to replicate the same scenario as our expert drivers we do in the proving ground. So basically, we define 2 model variants, one without an anti-roll bar and one with an anti-roll bar, and we run 2 optimization loops with the same load cases and the same targets. So it will be similar to this, our expert drivers working on the 2 variants separately to tune the vehicle depending on the decision. And what we obtain from this optimization is basically 2 different variants with 2 different sets of component specifications like springs, dampers, etc. And by doing this, we are able to basically in the end to quantify how much the performance was recalibrating by not including an anti-roll bar, and then how much the target needed to be changed, because we get to assess the performance results and the KPIs that we have defined in the process. Finally, a decision was made not to use an anti-roll bar, and that was again possible thanks to the use of the virtual proving load cases that gave us confidence about the assessment of these 2 variants in the virtual environment. So now Mr. Tosalin will explain how this approach applies to some other activities. So Guido, please, the screen is yours.
Thank you very much, Javi, for the introduction. So the next section is about ride comfort development, which is one of the most logical application for the virtual proving ground. So in this case, the kind of process that we follow is very similar to what has explained Alfonso before me. So the only thing is that in this case, we want to go to a higher level of detail in the definition of the components of the chassis that we want to then later assess in a physical tuning. So this stage again requires a model, but in this case will be a higher fidelity model it still requires our virtual proving ground surfaces, but in this case, we are using 3D models. And of course, we will go through an optimization process in order to achieve a definition of the detailed components which fulfills the performance targets. So the kind of simulations that we do is what you can see in this animation, in which we have a three-dimensional surface running on a vehicle model, which represents in high level of detail the chassis and the components. So among the three ingredients that I mentioned before, the model, the scenarios, and the KPIs, and the optimization process, let's start with a more detailed explanation of the model. So the model that we need will be a model in which we have a higher level of fidelity. So for this kind of simulations, we need normally a multi-body model, which includes flexible bodies, includes the powertrain suspension, which is a very important aspect. We need also a high level of detail in the definition of the bushings, which will need a certain level of frequency dependency, and the same goes for the dampers. And of course, we need springs and anti-roll bars. Regarding the road model, we use normally CRG files or RGR files. Basically, we need a regular grid, similar to what explained Gunnar before. This is obtained by laser scanning. For ride comfort, our standard is to use a 5x5 millimeter grid, and on which we have a 1 millimeter accuracy. So the other important aspect is the physical tire model. So the physical tire model in this case is required in order to have a correct enveloping of the obstacles, a correct ground to tire contact surface. We also need to have a high level of frequency, so high frequency domain simulations. And at the same time, we also need the tire model to be anyway efficient from a computational point of view. And for this, our preferred choice is the F-tire model that we can see here an animation of this tire model running on our pavé. So when using this kind of models, the big advantage that we have is the fact that we can achieve a very high level of correlation. So we can get a very high level of correspondence between the simulation environment and the reality, because we are using a high detailed vehicle model on exactly the same surfaces that we also have in the physical world. So here I will show you a couple of examples of correlation of between testing and simulation on a U-shape impact, something extracted from track number 7. And on a random surface, we have here an example of a correlation between testing and simulation in the badly maintained road, so track number 3. So as you can see, we are achieving in the simulation levels of accelerations which are very representative of what happens in the reality. So what is the scope of such level of detail? The main scope is to be able to use scenarios and KPIs, key performance indicators, which we extract from benchmarking. So let me start with how we define a KPI when dealing with ride comfort. So the KPI is normally defined by 3 aspects. The first aspect is the surface that we are using and the speed of the vehicle running on such a surface. The second aspect is a reference point. So we normally define a certain number of points in which we evaluate accelerations. Then the third aspect is the direction. We normally measure acceleration in the longitudinal, vertical, and lateral direction. And the last aspect is the kind of post-processing that we do on the raw data, which means which kind of specific numerical value we extract from a time series. In this case, for instance, we have a number of, we have made an example in which we are observing a peak-to-peak. Peak-to-peak is a typical value that we use in order to extract one numerical data out of a time series. So the combination of these 4 aspects define the KPI. And we normally need many KPIs in order to define in a complete way the ride comfort performance of a vehicle. And we normally extract these KPIs from benchmarking done in our proving ground. So for example, for primary ride, we use certain sections of the general road. For the impact comfort, we normally focus on track number 7, and we use different kind of inputs, positive, negative, U-shapes, etc. And for secondary ride, the random surf comfort, we use normally the badly maintained road, the rough road, the pavé, and the smooth road. We normally use a smooth road, which we can find in the high-speed track. So this is, let's say, the definition of the KPIs. And as I said before, it's exactly the same in the physical environment when you do the benchmarking and in the simulation environment, thanks to the virtual proving ground. So the optimization process goes in a specific way, which involves the fact that we, of course, start with a certain set of data that we have in the model, which comes from historical data. And it starts, of course, with our performance targets that we have defined based on the specific requirements for the vehicle and based on the competitors. So the first phase that we apply is a kind of an exploration phase in which we use a reduced set of scenarios and a reduced set of KPIs. But on this reduced set, we evaluate a large number of variants. So we evaluate a large number of different configurations for all the components. After we have done this exploration phase, we take the most promising sets, and on those we run a more detailed analysis, including a higher number of scenarios and a higher number of KPIs. So in this case, of course, because the simulations will, each variant will take a longer time, we normally evaluate just a selection of the variants that, as I said before, a selection of the variants which comes from the exploration phase, so that we can still manage the simulation time. So the objective is that out of this phase, we will define only a few number of variants and a few, let's say, a reduced number of components that we actually want to test in the physical tuning. In the physical tuning, we don't rely anymore so much on the objective KPIs. We rely mostly on the subjective evaluation done by the driver. And the big advantage is that, of course, this requires, as in the physical world, every variant and setup change will require a higher, longer time, but we will not have to evaluate so many variants because we have done this selection process in this virtual environment. Let me explain a little bit this through a practical example. So this is a case where we had to optimize the ride and handling for a mid-size SUV. And we have used the virtual proving ground exactly for this scope. So we have done an optimization loop in the simulation environment between the first and the second loop of tuning, because we have observed during the first loop that we had a number of things that required further optimization. And we have used an existing Adams model that was validated with the data obtained in the first loop of tuning and the FN1 F-tire model. During the simulation phase, we have improved the primary ride and the body control in the low frequency area, and we were also able at the same time to improve the area between 3 and 10 Hertz. And finally, we also reduced the impact acceleration. This has been achieved by defining a new lower control arm bushing in the front suspension, by also defining a new control blade bushing, and finally defining a new, let's say, configuration for the springs and the dampers. So then this vehicle with such tuning was evaluated in a second loop of physical tuning, and we observed that in the second loop it was actually possible to improve massively the performance of the vehicle, and that is also because we were able to select the right components in the virtual phase. And then let me also go through the other use case, the third use case that we are presenting today, which is related with the driving simulator. So in the driving simulator, the main difference compared with what we have seen before is that we are using our proving ground not only as surfaces, but also as visuals. And this makes it possible to actually drive the virtual model interacting, making an interaction between the driver and the virtual model in real time. So we are actually driving the vehicle in a scenario which is composed by both surface and visuals. So the main objective of this is to be able to have a clear understanding of the vehicle performance from a subjective point of view before we have any prototype available. And as you can see in this video, the synergy between the physical and the virtual testing in this case is very optimal, because we can get exactly the same kind of sensations driving the vehicle in our proving ground and then driving the vehicle in the driving simulator. Our driving simulator, as you can see, is a VI grade system. It's a DIM 250, which is composed by 9 actuators, which provide, let's say, a high level of displacement for the low frequency motions and a very high level of frequency response for the ride comfort applications. So, as I said, why do we want to evaluate a vehicle on the driving simulator? So the idea is to be able to have some sort of human feedback before the prototypes are available. So the main question for a driving simulator is whether it feels like a real vehicle. And in order to answer to this question, we think that the virtual proving ground plays a key role. So in reality, so the real thing is that the physical vehicle and driving simulator, they don't feel exactly the same. So there are some relevant differences. So the real vehicle provides a direct feedback of its behavior to the expert driver. Instead, the driving simulator provides a feedback which has some sort of more complicated journey. So the main reason is the fact that we have a motion queuing. There is some platform response. The platform always will respond with a little bit of latency and with a little bit of, let's say, compression of the motions. And we also have every aspect related with the model correlation and with the model fidelity. So of course, the two things are not exactly the same. However, an expert driver is capable of understanding how the real vehicle is based on the evaluation on the driving simulator. And this is because it can build kind of a mental model which translates the feeling and the sensations in the simulator into sensations that he would have on the real vehicle driving in the physical proving ground. But so how the drivers can be able to build such a mental model? So how can they understand and translate the feelings on the simulator into decisions related with the physical vehicle? So this happens thanks to the proving ground. So the idea is that we want to have reference vehicles and reference tracks that we use in order to define such a mental model. So in this case, what we will do is that we will use our virtual proving ground with a reference vehicle model, and the driver can then later drive the physical vehicle, which is fully which is basically the physical twin of the model on the physical proving ground. So making this reference driving, the driver can really understand what are let's say the differences and the similarities between the driving simulator experience and the physical driving experience, and he can build this mental model and finally get the full advantage of the driving simulator. So in a typical project, this would work like this. So we will use the reference models to take a reference. Then we will have our target vehicle that we are developing that will be used as the baseline vehicle model that we want to improve. This vehicle model will be driven straight after the reference model, And we will then, based on this baseline vehicle model, we will evaluate a wide set of variants in order to finally select the best combination of components which provides the best feeling and the best performance. So in this case, let's say we have the entire process covered. We validate the motion queuing with the reference model. We adapt the drivers to the driving simulator experience through the reference model, and we set the solid baseline for the evaluation of the baseline vehicle and of all the variants. So we have proved that this actually works with some projects already, and one relevant example is what I am showing in here. In this case, the objective was to be able to optimize the damper curves on the driving simulator before a physical tuning that was happening later on. So these, in this case, the drivers were allowed to take a subjective baseline with the reference vehicle model on our proving ground. And then later in the driving simulator, they evaluated the vehicle on a public road that we have here available, so La Giuncosa, and on the ride comfort tracks of the proving ground. During this virtual tuning, we generated several variants of the base damper according to the driver's feedback. And finally, we came up with a damper configuration that was provided to the supplier, who provided, let's say, the correct component properties to be then later evaluated in the physical tuning. And the good thing is that the agreement between what was evaluated in the simulator and what was evaluated in the physical tuning was very good. Meaning that we had to spend a very short amount of time in the physical environment in order to achieve the final damper configuration. And of course, also the bigger benefit is that we had all the let's say the damper components available to achieve such properties. Okay, so this is the end of the third use case, and from this point onward, I will give the word back to Javier to go to the final one. Thank you very much.
Before the conclusions, we have a final application, which is the application of the CRG or equivalent surfaces for vector roll load data cascading. Usually, this is a typical activity done during the development programs. And the challenge is usually is that you don't have a proto vehicle available at a time, or it's not really representative of the final intent. That at that time, the maturity of the components information is not really realistic enough. Or sometimes it happens as well that the active suspension influence needs to be taken into account, but the active suspension development is not ready enough. And as well, it's not possible physically to measure all the component loads that you will need for the fatigue analysis in simulation. What it allows as well is to test very efficiently more vehicle configuration that is not possible in the physical world, as well as perform what-if studies that are really helpful for the design teams. The IDIADA methodology on top of that is to take this correlated multi-body model that has been used for comfort and extend it the component properties for the ranges adequate to these new load cases. So starting from the road, then the durability team usually defines the durability cycle. So we compose this in the virtual world, and we run our multi-body model, which is valid up to 75 Hertz in these kind of surfaces. We cascade the loads, and this is transferred to the design teams in order to impose those loads into the chassis or the body in white models. And this has been described for durability applications, but it's quite similar for MBH applications. For these kind of simulations, there are two main possibilities to introduce the data into the model. One is the traditional time domain, where we have the physical representation of the road surface for the different kind of surface that we can see in the slide, and we introduce it on the contact patch as real geometry. Secondly, there is a second possibility that if you work directly in the frequency domain with its implications and limitations, you can be much more efficient from the time point of view. And what you need to do is to convert your real geometry into PSD that has the velocity into account as well. And this PSD is imposed as a boundary condition on the contact patch as well. And this is also something that is possible with the data available at IDIADA. What is more, we want to emphasize that virtual proving ground is also opening new and new applications at IDIADA, apart from the tradition that we have been already commenting. In this case, we would like to introduce you to one of the durability applications that we are working on. Usually, the durability cycle definition worldwide, it's a very costly and time-consuming activity because it implies a lot of logistics, a lot of big lands, etc. And it also involves the correlation between the market and the proving ground, which is also time and consuming. So from the RLDA, from the definition of the UR rows to the particular definition in a particular market or the specific rows to use, instead of using a conventional approach based either on physical measurement of the loads of these particular roads or a virtual 3D application, so similar to physical but in simulation, what we're working on and have defined is a virtual 2D approach where it's much faster and much easier to scan. And with this, we can run thousands of kilometers in order to define the key roads that later on, just a very short selection of them is simulated in a conventional approach in order to derive the loads. This allows to reduce importantly the cost and time of the process. And obviously it has some implications of accuracy, but it's a very well trade-off between them. As an application of the virtual road data cascading, we would like to introduce you a light track project that we conducted some years ago. As you can see in the video on the bottom right, what the end result and goal was to generate laboratory equivalent component tests for the chassis and the frame and the different bodies on the model. What it involves as well is high level of correlation of the multi-body and virtual program simulations for both durability and misuse load cases. We conducted obviously model building, correlation of the model for different load conditions, as well as the exporting of all the component loads in each load condition. This allowed finally to perform a load sensitivity analysis for the components for the different load conditions of the vehicle. We achieved also a meaningful correlation of the strain gauge at the different components, which in the end supported a proper fatigue prediction and correlation of the fatigue performance of the components. And finally, in order to reproduce component tests meaningfully, simplified and meaningful load blocks were exported for the test engineers. So just to finalize with a summary of what we have seen in this webinar, let's talk about IDIADA Digital Twin is a very good engineering tool to help the engineers to reproduce real tests in a very safe and efficient way, which builds a lot of confidence simulation, and you're able as an engineer to generate more data and in order that you finally get into better engineering decisions. The data of the virtual proving ground is available in for multiple applications, multiple formats and accuracies. So it's the main intention is to be very adaptable and flexible to the end need. And it has been demonstrated that these virtual proving ground methodologies are covering all the phases of the vehicle development, from 2D simplified 2D profiles to tuning and validation activities in the simulator, where you have a complete 3D environment. So we'd like to end the webinar by asking each of you, how can Applus IDIADA Digital Twin can fit in your simulation workflow and how we can support you. So thank you very much for your attendance today. We end here the webinar, and please don't hesitate to contact us for any further questions. Thank you.